All right, let's get started for today's webinar. Today we're going to be talking about Apache Doris 4.1, and that now it is available for public preview on VeloDB. So if you're looking to get your hands dirty, trying out the new capabilities that helps you advance your AI analytic workloads, there's no easier place than to try this on VeloDB Cloud starting this week. Today, I'm going to kick off by going through the new AI and retrieval capabilities that have now landed in public preview. And those of you who are following the open source release is already aware that we have added the IV and IVF indexes, the vector indexes, to the open source release. And primarily, this looks to solve the problem of how to handle efficient retrievals when you have billions of vectors at scale. Because using the HNSW index will result in a huge memory usage and therefore a very large infrastructure cost. Just off the bat, without any of the other optimizations I'm going to go through later in the presentation, the HNSW index already is 30% overhead over purely just the actual data itself. Actually 30% of that is in the graph versus the actual vectors, which only takes up around 70% of the actual storage. IVF actually reduces that back down to more of a normalized baseline. And then with further quantizations and the ability to actually store some of the vectors on disk, this memory requirement can shrink down to less than 10% of what you would actually start out with. What this really means is that instead of using potentially 10 servers or hardwares to be able to support your retrieval workload, you can now do so with a much, much smaller footprint. So let's dive into exactly what are some of the other things and how IVF works to accomplish that. If we look on the left side with the HNSW index, it requires a traversal through all the different layers and the entire graph to search through all of the vectors and distances. So that means you're actually reading a lot more data, hence this is going to require more memories and also, of course, latency. With IVF, what essentially is being done here is that instead of traversing through all the vectors, we first cluster the vectors into centroids so that when you perform a retrieval, you only have to focus on the centroids that are actually closer in relevance to what you're looking for. And what this looks like in SQL, in Doris 4.1, is very simple. When you're creating the index, you simply just need to identify the index type as IVF, metric type as L2 distance, like other vectors, and your dimensions and your endless. And it's very straightforward to get this started. So if you want to try the new IVF index, very easy to do so. But this index alone isn't where the efficiencies end. Another thing that we have been doing is really to think about, okay, if memory is the issue, how can we actually reduce memory? One easy way is to not store the vectors in memory and figure out a way to enable retrievals while the actual vectors are on disk. And for that reason, that's why we introduced the IVF on disk function. So now, if you actually indicate IVF on disk as the index type rather than just pure IVF, then the actual full list of indexes are actually stored on disk, and only the centroid, the point which indicates that these are different clusters, are stored in memory. The reason for this is because when you're reading through memory, it is 200 times faster than trying to scan any of the data on disk. So we want you to find the centroids quickly, and from there, pull the actual relevant vectors from disk, whereas the actual data can still be stored in shareable object storages as well. So this kind of tiering helps you to reduce the actual memory usage down to about 10 to 20% of what you would if you had to load all of this into memory. So the question here is, well, you're going to have to suffer some recall accuracy, right? But actually, even with IVF on disk quantizations, sometimes the actual retrieval and recall accuracies is negligible. And this can be further enhanced through some of the capabilities that Doris and VeloDB already offers through 4.0, such as mixing hybrid search and progressive filterings to boost the recall accuracies while still maintaining a relatively small footprint. Now, additionally, aside from using IVF and IVF on disk, we also offers product quantizations in different scalars. The typical one that is often used to try to boost efficiency is using the int8 scalar. The way this works is we look at a vector value, look at the min value, and look at the max value. And then we try to fit all of that value between 0 and 1, so normalize to between 0 and 1. And then we multiply that by an 8-bit integer, so in this case, 256. And then round it to the nearest integer value. So that way you're effectively doing a compression down to 8-bit, hence the actual memory reduction. You can also do this to a 4-bit integer for a greater compression, but there you do start to see recalls degrade. And also, of course, there's also binary, but generally speaking, int8 is a good one to use for minimum recall degradations. Another way for us to really think about the workloads that has to do with some of these knowledge retrievals is typically when we think about agents these days, looking to get context. Concurrency and speed is really important because a lot of times these searches are done in parallel. So the QPS, the queries per second, becomes an important metrics to look at when planning workloads. And on this front, we also introduced a feature to accelerate the workloads on this dimension. And this is done with something called the A index only scans. So instead of reading through all of the float columns, all of the actual dimensional vectors and compute the exact distances, you can actually search the quantized vectors in memory, therefore skipping a lot of the actual column read itself. And this saves a ton on the I/O front, allowing you to reach higher QPS without significant recall degradation. And this is, of course, paired with the quantizations on the previous slide. So not only do you get a smaller hardware footprint, minimum reductions in your recall accuracy, you also get to experience good concurrencies with this particular setup. And all of this is, of course, defined through SQL, so you don't have to do this in a different language or use any sort of glue terms to do that. So that's really key sets of capabilities that for the retrieval front are really making it so that it is efficiency remains as you scale to larger and larger data sets and knowledge sets. Along the line of working with agents and AI workload in particular, one of the patterns that we notice is that sometimes you need to mix SQL queries with actual full text search because you may be looking for a particular retrievals of text, but then you also want to pull the metrics that are related to the terms. Typically, in legacy systems, this requires two different databases. You may want a search database to actually retrieve the relevant text from a corpus. Could be documents, could be logs, etc. And then you would load that data into an analytical database to do the filterings, joins that will give you an insight. With Apache Doris and VeloDB, we've added the inverted index feature so that you can do this in one place, but it wasn't as elegant of a solution. It would still require you to perform searches, maybe deal with different syntaxes. However, with the search function, this can all be done in a single SQL statement. You don't actually have to write different statements. You can do this all in one place. And here we have some examples showing how this actually works. So if you look at the command on the right, we're basically searching for a message called CUDA out of memory. This could be an indicator when we're observing a GPU systems doing trainings or other things. And we want to find out, okay, like how many of these errors, what are the metrics that are out of the memory? So we want to look at the average memories and so forth. And also we want to be able to match these messages to the state of particular machines or aggregates. And you can do that now with a single statement where you can look for the counts, count the stings, averages, and that are associated with this particular log where there's a message called CUDA out of memory. And all of this follows the Lucene syntax with BM25 scoring. So if you were doing this in a dedicated search database, not much has changed, right? You can still use the same logic as you had before for this new capabilities. And this works with the variant data type as well as subcolumns. So nested JSON also works with this search function as well. So really, really exciting. That makes it working with multimodal data much easier within the SQL context. Along with working with some of these AI workloads, one of the things that comes about, and particularly with observing what is happening in evaluation, is the fact that the objects and payloads are getting much bigger. If we think about the context windows as a payload, 1 million context windows is around 4 megabytes already. And if you have multiple turns of a conversation, this can quickly balloon. And this really matters, and I'm going to go into a little bit more details in the next sections on handling semi-structured. But the problem here is if you don't have this, if you have a retrieval that requires you to pull the full payload, and this is actually split up into chunks, it will actually slow down the retrieval aspect of it. So if your workload demands retrieving the whole payload that it contains these different terms of conversations, particularly could be added length views and things like that, having a single JSON object with all of the data and the payload is going to speed up the retrieval side. And with that, I'm going to shift into the next section and transition into semi-structured data handling and talk about what are all the improvements in this particular areas coming off of some of these bigger JSONs. So when we talk about working with some of the payloads that we're seeing with agents, one of the traits that we've seen is ultra wide because there are so many different dimensions, so many different attributes, so many different SKUs that you could be looking at. What ended up happening is we see columns that are getting wider and wider. In fact, sometimes up to 10,000 columns. And this trend is fairly well known, even when we're looking at the data science days. Even if you're looking at zip codes, the number of zip codes can also balloon out of control. One of the issues when we're processing data that has a lot of column is really the metadata overhead. If there's a footer with every single column, in the previous version of Apache Doris, we had to read all of the footers ahead of time before actually processing a lot of this data. And so that accounts for a lot of the overheads and can actually slow your analytics down quite a lot. So with version 4.1, we actually separated the metadata footers and the actual columns. So we are only reading the footers on the relevant column for retrieving. And this matters because now you're reducing the amount of data that you have to read prior to the queries, significantly reducing your overheads quite a bit. So instead of reading up to potentially megabytes of metadata before reading a single byte of data, now you're dealing with 40 bytes per footer, a lot faster when you're doing these sparse retrievals. And the way we were able to accomplish this is actually with a new data format called segment V3. So prior, we had something called segment V2. Now with segment V3, we're able to essentially define the load patterns based on what I just described prior, which is not to read all of the footers ahead of time, but only during execution. And the way that you can actually set this data format is really simple. It happens when you create your table. All you have to do is set the storage format to equal to V3. And another thing to note is that this change only impacts all the new tables that you're creating. For any existing table, they will still adhere to the logic in segment V2. So just to know when you're looking to take advantages of these capabilities, you do want to create tables with storage format V3. So what does that mean essentially? It means that we can actually open these segments 16 times faster. And because we're not loading all of these additional metadata, it's actually up to a 60 times memory reduction when we're dealing with these ultra wide tables. And this approach follows the lens and the vortex formats, these which are open source, open table formats. So the logic is relatively consistent when compared to industry best practices. Additionally, one of the things I mentioned when we're dealing with these large retrievals, whether that's large objects or ultra wide, is that there's actually two patterns here And they're actually opposing each other in terms of how to optimize for performance. When we're dealing with these large tables, one pattern that we just went through is sparse read. I'm only reading two columns out of the 10,000s, or I'm only reading a subset or a small set of subcolumns in a larger nested JSON or variant type. And the other one is I want to retrieve the entire set of data, all the columns, or the entire nested JSON or variant. And the issue here is that if you're trying to retrieve sparse, it is often more efficient to have the data coded in variant so that you can retrieve all of the subcolumns directly, so you can skip reading a lot of the data. But if you're looking to retrieve the whole thing, then this gets to be a problem because you have to stitch together all the individual columns back together to reconstruct the original. So for this particular challenge, we created something called dock mode. So when you enable dock mode, we actually we defer some of the compactions and extractions until retrieval. So you actually have the originals also stored. Now, this does duplicate storage, but if you were trying to retrieve the whole thing, instead of having to restitch together the variants back, you can actually just get the original, improving retrievals much faster. At the same time, because we have already, if there are certain paths that we know are hot path, then you can actually configure it to be reading the actual subcolumns directly. And of course, for everything in between, the long tail of things, we try to use a hash shard sparse storage so that scans can be parallelized when you're doing ad hoc searches or something that's less predictable that you haven't extracted into the hot path. And at the same time, you don't really want to retrieve the entire payload, rather just a different subset. And through these three optimizations, we hope to be able to handle retrievals for these different patterns in a balanced approach, whether you're trying to retrieve the whole payload, a subset of the payload, or a random search. And this is typical of modern AI workloads, which become much less predictable in terms of what search and retrievals that are happening at any given times. And looking at a, potentially ultra wide, you can have a number of different paths as it scales out. So be on the lookout if you have these interesting retrieval patterns on the same data set. This should hopefully make things a lot faster across the board. Speaking of fast, one of the things that is core to Apache Doris and VeloDB is performance. We are a real-time analytical database, so performance and latencies is really important because ultimately that's what we're measured by. So with each release, we want to share some of the performance improvements that has happened here as well. The first thing is I like to share that across the board in terms of decision support queries, TPC-H, TPC-DS, and also SSB, which is the SAR schema bench. So these are all analytical queries that require joins and so forth. And across the board, we have seen improvements up to 22% in TPC-H and overall lift across the board. And this is, of course, using the normalized 4.0 as a baseline. So we're comparing against 4.0. Of course, this is done through the best of 3 runs on hot, and this uses a default configuration that I have more detail in a blog related to this release. So be on the lookout for that if you're looking to dive into the benchmarks in more detail. So where does this performance come from, right? Because nothing comes for free. And this comes through quite a few different things. As we're looking at decision support queries, join is one very important aspect that we want to improve on. And with the 4.0, we've added the aggregation pushdowns before join. So instead of looking to retrieve the entire facts, which requires scanning through all of this data, we can actually pre-filter on the facts so that the join only happens with the amount of data that's necessary. You can see the diagram over here. If we're querying a table with 1.2 billion rows, and there's another table that we're looking at with maybe potentially only a couple hundred dimensions, previously you would have to scan through all of the fact tables, find the relevant keys that match, and perform the join. In this case, we actually don't have to do that. So at the time of joins, instead of actually doing 1.2 billion rows, we're actually looking at 40K rows. So a much, much smaller amount of data that goes into the join itself, Hence, we're able to speed up a lot of the performances there. And just some anecdotal stuff to look out for across joins. This is about 200% improvement across the board. And again, this requires you to not act, to perform no changes to actually your queries. This is purely on the optimizer side. And in fact, we see about 50% of the test cases see more than 50% improvements, and in some cases, even seeing over 100x improvements, as you can imagine, the amount of data that you reduce from going into the join. Additionally, there are other optimizations that we have, and three in particular that I want to go through here. The first one is the case when. So when there's a lot of branching that happens, certain things slow down. So in this case, we are now applying case when rewriting for by default across the board. So this also offers a lot of improvements. And situations where this applies is an example here, where you have case when status 1, 2, 3. So for queries that look like these, this rewrites is particularly built for those particular situations. Another thing that we added is the nested column pruning. As we talk about variants and nested JSONs becoming more prevalent as a workload type, we're also looking to understand how to actually prune the data in a way to optimize reading through structures. So when a query touches one field, it reads that entire field, but we're really trying to prune as much, so basically not read as much of the data as possible when we're dealing with these nested columns, and in some cases able to achieve extreme performances improvements across the board by not reading the data in those cases through our optimizer. And finally, the last one is interesting for those who may be using materialized views or require cache to accelerate workload performances on the read side. So now you can actually set conditional and query caches. So reuse per segments filterings from prior queries. And this allows you to do intermediate aggregations. So if you already had a prior query that ran, you can actually now use some of the intermediaries as cache, hence accelerating performances across the board when you are relying on cache, particularly for acceleration. Hopefully, these three will make working with some of these new types of data structs easier and faster across the board. Now, lastly, I do want to touch on some of the exciting things that are coming through on Lakehouse and the core engines as well. So not only have we made improvements on the functions, predicates, and the optimizer, there are some serious things that go into the Lakehouse as well. A lot of this is around Iceberg V3, but I don't want to get into too much detail now. More detailed webinar on this is to come. But the biggest thing that I want to stress is how we're now able to keep the deletion vector from exploding over query time, and this is native for Iceberg V3. So Iceberg V2, if you're familiar with using Iceberg V2, every single delete write requires a new position to be added. And that's why we have compactions, right? Because as the number of pointers grow, you really want to compact this back down so that your queries doesn't slow down. With V3, which is really nice, is that now each data file gets one deletion vector bitmap. And this is merge in place. This is actually very similar in a way that Doris handles updates naturally. So we also use a bitmap that we merge in place for all of the inserts, upserts, and deletes. Except in this case, this is done on the Iceberg files directly so that the count of the actual number of delete files stay the same as the number of deletes increases. So this gives you stability on your query performances without compaction as you work with that table. And very, very important for real time as data changes quite frequently, hence the number of delete files that can balloon out of control. Some additional engine updates that allows us to do very cool things. And a lot of this really deals with working with time series data, as we notice that a lot of our financial customers are experiencing. One really exciting one is the addition of as of joins. So now you can do the nearest early matches. So imagine working with any trading data or trying to detect fraud through a time dimension. This gets more interesting and a lot easier to handle. Another thing is actually adding time zones to timestamps. I myself have definitely encountered issues where time zones have made my data relatively skewed. So now you can make sure that you're aligning to the right time zones so that time zone you don't have to do time zone reconciliations and corrections as you're working across different time zones in the world. We also had some things touch on nest, again, coming back to kind of working with nested data, so expanding arrays without ladder views, and then also introducing recursive CTEs. So for those particular queries, the hierarchical and graph path, you could now actually perform recursive CTEs as well. And with that, I wanted to do a final summary of all the capabilities that came out that are now in public preview. So that includes all of the new indexes and optimizations with IVF and IVF on disk, with vector quantizations, the search functions with the BM25 scoring, the 100 megabyte JSON objects that can now be handled in a cell, and then the segment V3s and the way that we're handling the different retrieval patterns with particularly documents and large payloads. Some of the and then the additional optimizer improvements, as well as the core engines that you just seen. Additionally, there are some experimental capabilities that are less mature, I would say, but are still there, such as the merge into functions for Iceberg, as well as the row lineages. So if there's any questions there, happy to dig into it a little bit further. Hopefully, we can get an expert to answer some of these questions there. Finally, if you wanted to get started on this, really, really simple. All you have to do is just to go onto VeloDB Cloud, and when you're creating a warehouse on VeloDB Cloud, there will be an option in a dropdown for selecting VeloDB Cloud version 26.1, which aligns to Doris 4.1. And once you deploy a warehouse with that particular versions of the Doris software, the cloud software, you will be able to experience all these capabilities yourself. And with that, that's all I have for today's webinars. Let me know if there are any questions. Savannah, any questions on the Q&A side? Don't see any. All right. If there's no other questions, there will be a follow-up blog that goes through all of this, and you can read about that and check out some of the links for additional detail. Furthermore, as this progresses, we will be back when this formally GAs so that you can learn about all the additional capabilities that comes with 4.1, as well as some of the new native cloud capabilities when this is finally formally available out in GA. But in the meantime, go try this capabilities out, try this with some of your semi-structural workloads, and let us know how we do. If there's no other questions, thank you everyone for your time, and hopefully I'll catch you on the next one.